So I want to thank organizers, of course, for the invitation. I will be talking about phase-sensitive tunneling in pnictides, review our work on it, because it's very important, of course, to understand the symmetry of the order parameter. But I first start with a brief note about a spontaneous Hall effect, which has been discussed already on this conference. And I will show you a result of Hall measurements on niobium copper cobalt multilayer. So this is lithographically formed object with contact. So cobalt is ferromagnetic, but in this case, the measurements are performed at zero magnetic field. There is no net magnetization of cobalt. So what cobalt does, it only introduces fracture. So linear defects, domains, which induces vortex and anti-vortices inside the material. So here you can see a longitudinal resistance as a function of temperature, and it's one and the same bridge, but the only thing which we are changing here is the current with which we measure. And what you can see, so if the current is low, this is black line here, you can see that the resistive transition is quite broad, and this is the consequence of this texture that is introduced by magnetic domains. So what magnetic domains do? They first of all introduce domain walls, which reduces the critical current, introduces vortices and anti-vortices, and now the other curves, we just change the current with which we measure. And you can see that there is a remarkable shift in the transition temperature. So I want to emphasize that this shift does not mean that we kill superconductivity by this tiny current. So what happens is that as we increase the current, the seeming onset of resistive transition shifts to lower temperature. But this is simply because this point corresponds to the case where the depending current becomes smaller than the transport current. And then it falls down to zero when the critical current becomes smaller than the applied current. And we can continuously tune it on wielding. So there is no suppression of superconductivity whatsoever here. It's just a transport effect. And it is interesting to see correlation with the Hall effect. Now, this is a simultaneously measured longitudinal transport and the Hall coefficient at zero magnetic field. I emphasize this. So this is a spontaneous Hall effect that we see. It's tremendous. It's huge Hall effect, which is because of it is induced by flux law. So it's flux law Hall effect is tremendous. So above TC, there should be some Hall effect due to the presence of ferromagnet. In fact, if you have a microscope, you would see it, but it's tiny on this scale. So totally dominated by flux law.
So what if you put it in terms of E square over H, how much is it?
It can be done, but it's not the point. It's so tiny that it's...
It's very tiny.
I mean, it's standard anomalous Hall effect. We see it. There is no problem with that. But it's orders of magnitude smaller. Now, what is interesting, where is the TC? Where is the onset of anything? So, if you look at the red curve here, so if I say that the onset of resistivity, well, onset of Hall effect, maybe somewhere here, we look at the resistive transition, nothing. So it's deep inside the kind of resistive state, very flat dependence. Now if you look further, so the onset of resistance here occurs somewhere in the middle of the Hall effect. So this is already deep inside the flux law state. Note that all this region is a flux law state. Now the question is, where is the TC in this material? Well, TC is in fact here. And you can, in fact, if you look carefully, you can see that there is, in fact, also a Hall effect here. It's going up and down, changes sign as it wish. And it is, if you zoom in, it is, in fact, much larger than the normal Hall effect. So you can see that there is a TC here. Well, it's kind of interesting. All right, now coming back to the subject about spectroscopy of pnictides. So what we know about pnictides, that it's a multi-band superconductor, so there is a common consensus about that. Of course, the question is, the previous talk, it was shown that the gaps are different at different bands. This is the early measurements with Andreev spectroscopy and also some of the early ARTES measurements for 1 to 2 material, which shows presence of 2 gaps. I however want to say that these results has been what is common about, what is conventional about unconventional superconductors is that results are very difficult to reproduce. So later measurements on the same materials by groups that are experts in this field could not produce the same results. So here is a recent result from the paper last year, which shows a single gap at around 10 electron volts. I think similar results were shown already here by Professor Wensburg with STM measurements, which show in this beautiful single gap picture. Well, what this is, the message is both from the previous slide and here, is that there is somewhat uncorrelation between seeing and believing. Not everything you see you should believe in, and not everything you don't see does not exist. So one has to be very careful with the interpretation of the data.
Here, the above a point contact, so below is a single particle tunneling, so they are different. Yeah.
I do not question the presence of 2 gaps. In fact, I will show you the data which will show the presence of 2 gaps. But there is a remarkable mismatch between some of the experimental data and the other experimental data. So general reproducibility is a problem. Anyway, multiband or not, I would say that this is not unconventional. Multiband is very common for all superconductors. This is my statement. And I will show you some results a little bit later. Which is more important is the phase of the order parameter, not the amplitude, but the phase. And we have seen a variety of different scenarios from S++ to S+- and a variety of them. Of course, it may depend, it may not be universal, it may depend on Dawkins, but we are interested to be able to measure this. Also, as was clarified by Sasha Balatsky and Hanika, wherever you have a multi-band structure, you should expect that there is an odd frequency superconductivity as well. What kind of phase-sensitive measurements were suggested? So it was suggested to use quasi-particle interferometry for looking at the gap symmetry, and this is again an example from Professor Wen's experiment, in which they see a beautiful quasi-particle interference from different bands. Of course, this quasi-particle interference is still only shows us an amplitude. But with some clever analysis, they concluded that this is similar to, consistent with S+-. But of course, it would be very good to have a direct probe of the phase of the parameter. And we know that Jolson effect is probably the only one that allows us to see it or probe it. And we have a beautiful example of a tricrystal experiment in cuprates. And again, cuprates is probably one of the most unconventional superconductors in the sense that the band structure is so trivial. So we have a single band, D wave, so by rotating the crystallographic structure, you basically change everything. Now let's take a look on pnictide. Now we have many bands, and if you rotate them, don't expect anything good. So there will be massive tunneling between different bands, different directions, different signs. I wouldn't bet that you get anything understandable out of this experiment. So we need to do something else. And there were some proposals. For example, Golubov and Mazin has suggested to combine a heterostructure with hole-docked and electron-docked pnictides, and then organize somehow a core tunneling experiment from hole to electron. from point contact to tunnel contact. I mean, all this sounds like a good suggestion in theory, but to my knowledge, there is no way to produce it experimentally so far. This type of experiment with point-like contact and tunnel contact has been made once. There was one attempt, there is a publication on that, but it was not reproduced. So again, what can you do about that? Well, first of all, yeah, and I want to say that there has been significant efforts to make Josephson junction with pnictides. However, the quality of those junctions are such that you can only study the physics of defects in those junctions, but not superconductivity in pnictides with this. So what we need is very high quality pnictide-based Josephson junctions, and that is the main motivation. So we spent some efforts on making a Josephson junction between a conventional niobium superconductor and pnictides. So those are C-axis Josephson junctions. So we take a single crystal, we cleave it, and then we do lithography, so deposition, lithography. So here you see an example, so the scanning electron microscope of the ready device. So here we have a crystal, niobium electrodes on top, and then junctions are formed at the intersection of the opening in the crystal. So this is the opening. The rest is isolated by silicon dioxide. So here are these painted in orange. Those are our junctions. You can see that there are multiple junctions on the crystal. So this is three-dimensional sketch of it. So this is how it looks like on a larger scale. So we have electrodes, bonding, and then put it in the crystal. So this multi-contact configuration of our sample allows us a variety of measurements. So we can, in fact, measure the in-plane transport as well, so by sending current from one junction to another and measuring voltage responses on other contacts. So we can measure longitudinal resistance. And by sending current through the junction and measuring on this side, so we can probe C-axis. So Josephson properties for this of those junctions. So here are longitudinal measurements of resistivity. So you can see transition from room temperature. So TC is around 30 Kelvin. So everything is as we more or less expected. So let me first start with transport measurements. So longitudinal transport measurements. So here you can see resistance as a function of magnetic field perpendicular, parallel. So we can extract up a critical field. So this material is not very anisotropic. So anisotropy is of the order of 2, which is consistent with other magnetic-resistive measurements. Now, my favorite tool is angular-dependent magnetic resistance. We rotate the sample in magnetic field. So in this case, it's 10 Tesla, and we change temperature. Look how the angular-dependent magnetic resistance changes. What you can notice that the anisotropy is low. So it's basically a three-dimensional superconductor. And if you look at low temperatures below TC, you see this flat curve, which is typical for 3D anisotropic superconductors. As we approach to TC, we start to see a cusp. So this is slightly above TC, in fact. And if you go to even higher temperature, we get an enormously sharp. So. Good. Nice. Now, what was that is the surface superconductivity. So there is a way to organize surface superconductivity just by applying magnetic field. All right. Now, junctions, C-axis properties. So we measured the junctions. So we looked at the area dependence. So there is very reproducible. Here you can see a Fraunhofer modulation for all 6 junctions. You see that this is a perfect Josephson junctions, very reproducible. Good. What we can measure is temperature dependence of the ICRN product, and it differs from the ambient carburetor.
Maybe I miscalculated when we started. Did I cut you? Did you just? We are close to 30 minutes, or do you double check?
It's just 15 minutes.
Only 15 minutes. Okay, sorry, I was confused. I didn't want to make your talk twice shorter than others. Yeah, please continue. Yeah, you have extra 15 minutes. Yeah.
Sorry, given that, can you explain that
Yeah.
cusp that you skipped over? What is the cusp?
Okay. The cusp is the surface subconductivity.
Yeah.
So, which is extremely robust in pnictides. So there is a very simple way to organize two-dimensional subconductivity in pnictides. I wanted to also say that we studied iron, tellurium, selenium superconductors. Unfortunately, our crystals were inhomogeneous, so it had 2 transitions. However, when we measure angular dependence of magnetic resistance, we clearly see 2 cusps appearing on each of the faces. So even though this material is very inhomogeneous, so we have 2 faces, each of the faces shows very clear, beautiful surface subconductivity.
So the cusp is 0 degrees is when your field is along the 2D.
Yes.
Okay.
Okay, back to
Can I add one point? So the cusp is just from the flux flow, right?
This is just from surface subconductivity. It appears
Why?
when the field is exactly parallel.
No, I mean
to
so that's the resistivity between different voltage leads, or from what?
It is flux flow. I mean, so it's
Yeah.
if you have a component
It
of
is
field
flux flow,
perpendicular,
I mean.
then you have vortices,
Yeah,
I think, and then that gives you resistance.
what kills, yes, but in fact there is no bulk subconductivity already at this point. It's only surface level. We can talk about it. So let me come to the subject of this talk. So Josephson effect. So we have a very good junctions, and what is interesting. So first thing that we can see is that the temperature dependence is different from conventional temperature dependence of ICRN product. And this is the first signature that this is a multi-band superconductivity. So this dashed line here is a simulation by Bumistrova and al., who calculated for S plus minus case, but in AB plane. So it cannot be directly applied to our work. I made a very simple toy model for C-axis ICRN product. So we have, let's assume that we have 2 bands, and in this case, when we make a C-axis junction with a conventional superconductor, so there will be tunneling from the 2 bands. So let's say that we have 2 channels from the 2 bands. Each of them is described by Abbe-Karabaratov expression. So, and then those channels, the critical currents add up together. The weight coefficient between those 2 channels depend on transparency of the 2 channels. So, from niobium to each of the bands separately. And then the total ICRN product is then a sum of the critical currents from the 2 channels. So that is the toy model. Now, if you look at the gaps, so for niobium, the gap is 1.5 millielectron volt. For BNFR, so we expect 2 gaps with something like 9 and 3 millielectron volts. And the critical current in some Abbe-Karabaratov expression, in fact, depends on the gap values. So for niobium case, it's this dependence, and for the 2 channels, it looks like this, but the shapes are slightly different. Now, if we would have S++ case, and we change the transparency of the channels, going from one channel to completely only the other, there is a minor variation in the shape of the critical current versus temperature. But if you start to subtract them, if you assume that there is sign reversal between the bands, then the situation becomes much more interesting. So now we go from one band, which is, let's suppose it has a negative sign, the other is positive, and then we start to compensate them. So when we add them, we subtract the total current. This is the result of the temperature dependence. The complete compensation appears at about 1.56 ratio of the transparencies between them. And if you look carefully in this area, there is a very peculiar one can expect very peculiar temperature dependence with a cusp. So it's actually going from positive to negative. In experiment, of course, you would always measure positive, which would show this cusp in temperature dependence. And this is entirely due to a slight variation of the shapes of the temperature dependencies at different depths, with different amplitudes. All right, so now what we do next, we introduce an interlayer of copper between niobium and pnictide. Now, this is now a superconductor normal metal superconductor junction. And what everybody knows that introducing a normal metal would introduce a proximity effect. And generally speaking, proximity effect should reduce the critical current of the junction. Now what happens here? So again, we have good junctions with very nice characteristics. So here you can see Fraunhofer modulation as a function of temperature. So this is the most beautiful curves that you may imagine. Shapiro steps, again, very clear Shapiro steps. The only difference is that you see profound subharmonic steps here. But this is not strange because you have SNS junctions in which the current phase relation is non-sinusoidal. So this is something that you would expect from non-sinusoidal current phase relation. This is ICRN product for those two junctions that we compare. So the red one is the niobium pnictide directly, and the blue one is the niobium copper pnictide. So there is some difference in temperature dependence. All of them are not S-type, so there is something. But this is a minor effect. What is the huge effect, however, if you look at the scales here? The ICRN product of niobium junctions, pure niobium, is 4 microvolts. For when we add copper, the ICRN product increases dramatically to more than 150 microvolts. So this is completely counterintuitive, because when you add a normal metal in a junction, you would expect the proximity effect which would reduce the critical current and not increase it. So this was really a puzzling phenomena that made us to scratch our head for a while. Now take a look how it happens. So if you look at so this is a table of all the junctions in the two samples that I showed. The critical current density for niobium pnictide junctions are in the range of 2 kiloamps per square centimeter, so typical joules in currents. Resistances per area 120 milliohm micrometer squared. Now, when we add copper, you see that the critical current density increases by more than a factor of 5, but also the resistance increases by more than an order of magnitude. So both resistance and critical current increase, which is very uncommon. And as a result, the ICRN product increased by a factor of 60 when we introduces the copper interlayer. Okay, so in order to understand what is going on, let's remind us how the tunneling into multiband superconductor would look like. So we will have to integrate spectral functions now as a function of momentum, because now we have to take into consideration a complex structure of the Fermi surface. So the density of states is determined via spectral function as usual. We have the c-axis joules and junctions, so we have to integrate in the AB plane, assuming that there is coherent tunneling with conservation of the in-plane momentum. Now, materials that we are talking about have very different Fermi surface structures. So for pnictides, we already discussed that there are 2 basic bands, or maybe more, but they are oriented, one in the center and then 4 in the corner. For cuprate, this is the most trivial Fermi surface, almost spherical in the center. And niobium is really a champion. It has an uncountable number of bands. I don't know exactly how many, 16, presumably, scattered everywhere across the Fermi surface. Okay, so we have to make a projection on the AB plane. So if we do this, it looks like this. So for copper, we integrate this over the AB plane. So it looks like this. So for niobium, it is this projection. However, we are dealing with polycrystal. So niobium that we deposit and copper are not monocrystalline, so they're polycrystalline with different orientations. Therefore, we have to average also with respect to AB plane. So rotate this pattern and make an average. So the average would look like this. So when we rotate this and take an average, you see that in copper there is a very clear sphere here, which basically reflects the spherical, almost spherical Fermi surface. For niobium, you can see that it's really almost continuously covering the whole Brillouin zone. Now, with this taking into account the band structure now of pnictide, we can calculate what is the weight factor of different bands. And this should be here. So for, let's start with niobium. For niobium, since it's very randomly, uniformly distributed over Brillouin zone, it will basically reflect the band structure of pnictide, almost one-to-one. For copper, however, you see that it will be greatly amplified at the edge of the Brillouin zone, while the center will be absent. So this phenomena I call band filtering. So band structure of the intermediate layer that we introduce is acting as a filter, filtering away specific parts of the Brillouin zone of pnictide. Now this explains our strange result that I have shown. So for direct contact with niobium, both channels from different bands are active with equal weights. And that leads to, first of all, low resistance, because there are two channels, resistance is low. However, simultaneously, it leads to low critical current, because if the bands are having opposite sign. So they are subtracted from each other. For copper, only one band is active, in this case, this corner bands. That filters away the central one, and that leads to increase of resistance, because one band is cut off. However, at the same time, it leads to simultaneous increase of the critical current, because there is no current cancellation. Well, I guess this is an indication, a beautiful indication of the sign reversal of the order parameter in pnictides. It is consistent with S plus minus order. And moreover, we can say that sign reversal occurs between the central and the corner bands of the pnictide. All right, I think I came to my conclusion. So we managed to make high-quality C-axis Josephson junction between niobium and pnictide. Josephson current is phase-sensitive, and in sign reversal multiband superconductors, the main phenomena is cancellation of currents between different bands with different sign. This is, of course, a big challenge for interpretation, especially if there is more than two bands, you have to take into consideration. But also, this is a possibility for investigation, and there are many parameters that are interesting to look at. For example, temperature dependence can be very unusual, as I emphasized, but also just the bare value of the ICRN product carries an important information. Our main result is this new band filtering technique that we have demonstrated. So by introducing an intermediate layer, we can select a specific bands in the structure, and it provides a new dimension in phase-sensitive studies of multiband superconductors. And our experiment with copper interlayer supports the evidence for the sign reversal S plus minus order parameter with sign change between central and corner bands. So thank you very much.